This conference will now be recorded.
Well, since I hope everyone is here and we have a lot to cover, we really should begin today's virtual conference day two, that is 8th European Congress on 3D Printing and Additive Manufacturing. A very good morning, good afternoon, and good evening, one and all. Virtually present here virtually with me today. Let me introduce myself. My name is Clara Bigblum, Conference Secretariat at Coalesce Research Group LLC, and I will be available for any of your queries or questions throughout the webinar to help you out technically and organize the webinar successfully. Um, Finally, I would like to thank all attendees and participants of today's virtual conference of day two and hope you enjoy the webinar and gain the knowledge from the sessions today. We also hope your participation will contribute to new research findings and that will lead to new collaborations and research initiatives. Before we start with the session, I hope some of you will be new to GoToMeetings app. Let me just explain you the important tools required for the presentation. On the GoToMeetings app or a web page, you can find four icons at the bottom center: mic, camera, screen, and end button. Mic button, click on that to mute or unmute yourself. I request you all to stay muted while our speakers are presenting their research work so that it does not cause any disturbance to them. Camera button, you can use this button to share or unshare the web camera. If you have the option to share the web camera, you can do it, and it's completely your choice. The screen button, you can use this button to share your screen. This is the main part during your presentation. After I call your name from your side, I will be making you as a presenter and will give the permission to share your screen. Then only you will be able to share your screen. So once I make you as a presenter, you can click on the screen button and you will find a pop-up window to share your screen. The end button, this is your fourth icon where you can use this to leave the session. On the top right corner, you can use the options to change your display settings. At the top right corner, you will have three icons: people, chat, and settings. In the chat option, you can chat with me or any other participants. For the settings, you can use this button to check for the settings of your speakers and microphone. So as I mentioned, kindly remain muted during the presentation so that the presenter does not get disturbed. And for any questions, you can ask the questions or you can send your questions in the message box too. Well, let's not take much of your time. Finally, I would like to request you all to please give us a brief introduction about yourself before starting with the session so that we can know about you virtually. Now let's move on to the first presenter, Dr. Surinder Pal from Atlantic Technological University, Ireland. Hello, Dr. Surinder Pal. Are you ready with your presentation?
Hi, yeah, very good morning. Yeah, I'm ready. Yeah, thank you.
Good morning. Now I'm making you as a presenter. Kindly click on the screen button to share your screen, please.
Yeah,
Yes, I have made you as a presenter. Can you please share your screen?
yeah, just give me a moment. Yeah, is it okay now? Yeah. Hello.
Yes, your screen is shared
Yeah,
now. You can start your presentation now.
that's fine. Yeah. First of all, very good morning to all of you, and thank you. Today I'm present my topic that is comparative milling machine-based stress analysis. So it's the analysis which I done using FEM, and it shows the stress variation while using the conventional titanium alloy and the additively manufactured alloy. So my name is Surinder Paul, and I'm from ATU, that is Atlantic Technological University, Sligo. It's in Ireland. Before starting my presentation, I will go through the content, the motivation behind my work, and the literature review, the machinability of 3D printed material, the conclusion, and the future recommendations are relevant to this topic. Before starting the motivation, now you see the 3D printing now it's very ongoing subject, and it's very broad now because so many people working on it, and there are so many things going on with the 3D printing material, especially with the titanium alloy. Here you can see the different parts of the material which are nowadays manufacturing with the help of 3D material, 3D printing machines. See the fuel nozzles, the engine blocks, the prosthesis. This is a very well advanced topic nowadays, and the turbine runner blade. Sorry. So further we go into like the implants, oil and gas industry, the chemical industry, the marine industry. So there are so many broad topics which nowadays are working and using the 3D printing technology to build the material. So, moreover, like the when we say the conventional material and the now the 3D printing, there are few motivations, and that's the main things which make different in 3D printed material apart from the conventional technology. It's like the advanced geometry now we can build and enhance efficiency because we are fabricating the material layer by layer. That's the basic definition of the 3D printing, and we can customize as per our required shape. It has a huge industry application. Sustainability, that's again a big concern for the industry because it reduces the material wastage and also the energy consumption as well. So it's a part of continuous innovations because there are so many ongoing research and development in this field which are further expanding the possibility, especially in the titanium alloy. Come to literature, I just mentioned a few literature as far the time is concerned. So it used in various industries due to its unique capability. So we can easily turn into desired dimensions. We can get a better surface quality, and yeah, but still, when we say the surface quality, as we get the 3D printed material, it have some pro and cons as well. So as the pro side, we can use the material, we can shape the material as per our requirement. But if we go for the con side, it has quite of low surface quality. So to enhance the surface quality, we will do some machining things, especially for the milling process. So machining is quite important after getting the desired shape of the additively manufactured material. So previous study indicates that the cutting forces, like especially with the 3D printed material of titanium alloy, is accelerate the tool wear, and it also enhances compromise the surface quality as well. So however, these all conditions help me to evaluate the research objective and the scope of this study. So in this study, I will investigate the impact of milling on which is side milling process, especially on conventional and additively manufactured. So the FEM model is used using the Abacus software. So JAC models, which are very familiar and which are very well known for the FEM analysis, especially in the machining as well. So the main focus of this study to understand the cutting forces of this of the material while doing the additively manufactured material and while comparing the previous the conventional material. So the insight gained from this research, that is main objective is to optimizing the parameter, because while getting the stresses value, doing this operation and getting the cutting forces would help us to improve the machining parameter and enhance the efficiency. So here you see the model I developed in the Abacus. So that's a milling tool, and we using a as a the geometry you can see that. So these are the geometry which I'm using. The depth of cut is considered as a 0.01 mm, that is quite low, but the cutting velocity is 90 mm per second. So these all parameter actually are selected by the literature. I went through few literature, and I get the parameters which also quite help me to uh, to to to to to compare the result with the literature, because these parameters has been decided with the help of literature review. Further, you can see that the in the image A we have the conventional titanium, and in the B section we have the additively manufactured. The property of this material I get from the literature, and this will help me to model the material and perform the whole operation with the help of literature review. So here you see the milling forces as I calculated. So milling forces in the additively manufactured titanium is quite large as compared to the conventional material. So this is how the variation forces actually obtained from the analysis. So further you see the stresses which I get. the path, the true path distance, actually the distance which I choose to get the stresses value. So here you see the difference between the titanium alloy and the difference, the 3D printed and the conventional one. So it's just the idea actually how the 3D printed material is quite more harder, and it will create more stresses while machining of the material. And this the same I mean the outcome of this analysis has been verified with the literature. It is also shows by these two authors, the Vixen and the Zioa et al., research, which has highlighted the same parameter while comparing the results. So further, it's just like the one directional, objective how we can carry forward with the same parameter, changing the stresses, changing the cutting speed, changing the depth of cut. But as of now, the additively manufactured material, it exhibit a strong, it exhibit a higher stresses value while comparing the conventional one. So a recommendation for the future testing, that we can do the test in a real life, like trial to milling percent, to ensure the computer simulations are right. Because actually, while changing the parameters, we can easily get the result in simulation, but we have to do the real life testing as well, because it will increase the cost. Nowadays, I the additive manufacturing material is quite expensive, so that's the reason actually people are doing simulation and changing the parameter. But still, the testing in real life is make a big difference. So we can try a different material, shows the 3D printed material react to different cutting angles. So angle is also again the further parameter for the future recommendations. So explore methods to improve the surface finishing. Yeah, still now the surface finishing is a big concern. So there are I have go through some literature where people are using the different machining technique like side milling, face milling. These operations, they will improve the surface finishing with the desired parameters. So that's all. Thank you very much. That's all.
Thank you, Dr. Surinder, for your presence and presentation. Does anyone having any queries? I hope there are no queries. Once again, thank you for your presence and presentation.
Yeah.
Okay, now let's move on to the next session. It is from Dr. Hamid Askani from Azad University Science and Research Branch, Iran. Hello, Dr. Ahmed. Are you ready with the presentation? Can you please unmute yourself?
Hello? Yes, I'm ready.
Now, okay, now I'm making you as a presenter. Kindly click on the screen button to share your screen, please.
Thank you. Entire screen. Okay. Okay, is the presentation visible?
Yes, it's perfect. You can start your presentation now.
Okay, thank you. Thank you. Greetings. Well, today's presentation is about selective laser melting technology, or SLM, in the manufacturing of biocompatible and automotive parts. Uh, the research was done by Omid Ashkani, Sinatari Nesanakian, Rahila Fadoi. The presentation outline includes an introduction to the SLM technology, the methodology of our research, tests and results, then afterwards discussion, and in the end, conclusion and further research areas. And the research area significance in our study is material based in manufacturing processes. The SLM method has proven to produce little to no material waste in the process of manufacturing. So it's a pretty interesting manufacturing method. High temperatures in manufacturing processes and energy waste. Again, it is related to the waste of energy and material. So SLM has proven to be a much more sustainable way of manufacturing different parts from a variety of industries, which of course is addresses the issue of global warming in the long run. And of course, minimal restriction in manufacturing of a variety of parts across the vast area of industries is another uh, pro of the SLM manufacturing technique. And manufacturing of parts with near net shapes samples, which we will see with our three different examples of parts in the different industries. Introduction to SLM technology. SLM is an additive manufacturing process that uses a laser to selectively melt and fuse metal powder, creating complex 3D objects layer by layer from a digital design. A high-powered laser is precisely directed onto metal powder, melting it at specific points layer by layer, resulting in precision-built components. And SLM works with metals, uh, many different kinds of alloys, which we have also used and utilized in our research. Well, this makes it valuable in different industries like automotive, medical, aerospace, and much more, producing customized and lightweight parts. SLM technology in manufacturing offers design freedom, reduces material waste, enables rapid prototyping, and often leads to improved component performance. But it also has its own challenges, which include post-processing and some material limitations, which, of course, with ongoing research, we are about to hopefully overcome these limitations. The methodology of our research. In the following research, a dental implant body was manufactured using the SLM method. Firstly, the dental implant body was reverse engineered from a physical sample. Afterwards, the 2D drawing and 3D CAD model of the dental implant body were designed using CADIA as the 3D CAD software. Secondly, the dental implant body was manufactured using a special manufacturing device, which we will see in its technical specifications going forward. The aforementioned steps were repeated for a hip joint prosthesis. The steps were once again repeated for an automotive part, which was specifically a steel rim, demonstrating the efficacy of the SLM method in the automotive manufacturing industry. As you can see, we will investigate three different types of products and parts in two different industries. The first being medical, the first and second being medical, and the third being the automotive industry. We can see the model of the dental implant body. The model on the left is the 3D CAD design, and the drawings on the right are the 2D drawings. You can also see the model of the hip joint prosthesis. On the left, you can see the drawing of the part, and on the right, the 3D CAD model, which were, of course, then produced using the SLM method. Biocompatible materials. In the following research, titanium alloy in powder form was chosen for the manufacturing of the final sample. The powder was sourced from the Tecna company. Since titanium is used extensively in this industry, a titanium alloy was chosen as the material of choice. The particle size of the powder employed in this study was 20 to 60 micrometers. As you can see from the illustration, the particles were all rounded so that they can actually get through onto the platform and then lasered for the proper uh, product manufacturing technique, which was the SLM method. If the grains, if the particles were uh, not rounded, they couldn't get through the nozzle. So then being rounded and with the right size, the manufacturing technique could be employed properly. The manufacturing device specifications. The You can see a table of the technical information of the manufacturing device in front of you. The layer thickness was 15 to 70 micrometers. The laser type system was 310 watts, a fiber laser. The scanning speed was up to 8 meters per second, and the manufacturing speed was up to 25 cubic centimeters per hour. Protective gas environment was mainly consisted of argon and helium, which was 75% argon and 20% helium, with a 5% of nitrogen. Gas temperature was 23 degrees Celsius, and the supporting table material was in stainless steel. The tests and results which we have run were as follows for all the three different parts. Hardness test was according to the ASTM E10. The dimensional test was done using the VMM, the scanning electron microscope, or the SEM, and the energy dispersive X-ray spectroscopy, or the EDXA, were all performed on the three following parts. The hardness test, as you can see, there's not much difference between the manufacturing techniques of cast and machining and the SLM technology. So there isn't quite an advantage uh, using SLM over machining. But the thing is that with cast and machining, you have tools that wear out, and also you have production waste, which you don't have using the SLM technology. So SLM has a clear upper hand in the uh, in this part. The dimensional test, as you can see, the parameters are as follows. The length for the uh, dental implant body was 10.7 millimeters. The external radius was 3.29 millimeters. The internal radius was 2.95 millimeters, and the wrench size 4.2 millimeters. Wrench radius 2.55 millimeters. Final angle of wrench was 30 degrees. CD1, or the first critical dimension, was 3.51 millimeters, as you can see from the technical drawings. And the critical dimension number 4 was 10 millimeters, which were exactly as our 3D CAD models. So again, in this dimensional test, we have gotten proper results. And the SEM, as you can see in the SLM, um, the microstructures are well rounded and non-porous as in against machining, which you can see the porosity is noticeable. So SEM, I'm sorry, SLM in the dental implant body is actually much more desirable, since the microstructure of the dental implant is such that when implanted in the patient's jaw, the uh, it can cause osteogenesis, and it can be a better pair to the patient's body in the end. The EDXMA test, you can see that the elements are as follows. Aluminium in weight percentage was 6.15%, and the atomic percentage of 10.45%. Titanium in weight percentage was 89.55%, and atomic percentage of 85.69%. And vanadium was in weight percentage of 4.29% and atomic percentage of 3.86%, which are to our liking. And you can see that there was no no other materials and no impurities in our final example production, which is, of course, another pro of this manufacturing technique. You can see the hip joint prosthetics sample produced using the FDM technology. We have not done SLM for the hip joint prosthetics, but we've produced a part using the FDM technology. And finally, SLM in the automotive manufacturing industry. We studied the utility of the SLM method in the automotive manufacturing industry and investigated its feasibility. We found out that this method of manufacturing can be utilized to a great extent in the manufacturing of the automotive driveshaft, which we will investigate in detail in our future research. We chose the material 304 stainless steel for the manufacturing of our part, which you can see, of course, with the 2D drawings to the right, and then the 3D CAD model to its right. We chose CATIA as our 3D CAD software of choice for the modeling and design of this part. The microstructure and hardness of the automotive part. Well, as you can see, both the microstructure and the hardness of our automotive part, which is small and is actually compared to the size of the automobile is it can't it's relatively tiny. So to be able to manufacture such a part with such precision is actually remarkable. Um, in conclusion, we were able to manufacture a medical grade dental implant body using the SLM technology. We showed that the hardness of the SLM manufactured part was the same as the cast and machine part. We showed that the microstructure of the SLM manufactured medical parts were porous and round, which may help osteogenesis. We showed that virtually no manufacturing waste was produced using the SLM technology. And we demonstrated that this technology can be utilized in the manufacturing of different parts across different industries, for example, medical and automotive industry with minimal manufacturing waste, which are, of course, way more sustainable in the long run and thus are more to our preference. Future directions. Further research can discover new applications for the SLM technology. Further research can investigate the manufacturing of a variety of other biocompatible alloys using the SLM technology. For example, titanium, magnesium, titanium magnesium, and titanium magnesium and copper alloys. Future research can investigate the cytotoxicity of the SLM manufactured medical parts. Future research can also investigate the wear resistance of the SLM manufactured parts. Thank you for your attention.
Thank you, Dr. Amit, for your presence and presentation. Does anyone having any queries? I hope there are no queries. Once again, thank you, Doctor, for your presence and presentation. Now let's move on to
Thank
the
you.
next presentation is from Dr. Abhay Meena from Lok Nayak Hospital, India. Hello, Dr. Abhay Meena. Are you ready with your presentation?
Yeah, I am ready.
Okay, now I'm making you as a presenter. Kindly click on the screen button to share your screen, please.
Yeah,
Do you got any pop-up window, Dr. Abhay Meena?
yeah, I'm not able to share the screen.
May I know which device you are using?
Yeah, it's coming, I guess, now.
Yeah, the screen is shared. Can you make it in a presentation mode?
Yeah, yeah. Hi, it's visible to you?
No, the full screen is not shared. Can you please unshare and share the entire screen? Can you please
Just a
open the
minute.
GoToMeetings app and share the entire screen?
Is it visible now?
Not yet. Yeah, it is visible now. You can start your presentation.
Thank you. Hey everyone, I'm Dr. Abhay Meena. I am orthopedic surgeon. So we used spawn tumors. Uh, uh, Here are some of our cases are there. Like chondrosarcoma or radiotherapy sensitive, but a significantly large tumor and surgically treatable tumor at the pelvis, higher local recurrence rates of around 30%. In this anatomy region, it is difficult to obtain a adequate with the complex 3D geometry of the pelvis and close proximity to the vital structure. Safe margin may not be reached. Procedures require meticulous preoperative planning. So this is our first case, pelvic bone. A 33-year-old male presented with large abdominal swelling in the right iliac fossa and plain right iliac blade with patchy calcification. This is the tumor. Swelling size was around 20 iliac fossa to the right hypochondrium. Like it's very big tumor. This is the X-ray of that patient. Like large multilobated tumor. So these are the tumors. What planning was digital imaging, and the 3D model was created showing relationship between the pelvis and the great CT scan MRI, and we fuse them. So this is the fuse picture of CT scan and the MRI using the three, and then we have created the osteotomy jig for tumor resection. This blue one is the, so we have 3D printed that jig, and we have applied on the precise tumor resection. So we have applied that jig on the bone tumor. This is precise resection was done, and the specimen size was 20 into 15 centimeter. So patient is doing well after that. Old boy presented with swelling on the dorsum of the left shoulder since 3 months, and on biopsy we have and virtual 3D model of the normal scapula made. Then scapula of the normal side. So same side scapula was created after mirroring. Put holes for the muscle attachment in the that model, and then we have printed. This is made of titanium, made by computer assisted subtractive manufacturing was done. We have and we have put that uh, tumor prosthesis of a scapula. Of the chondrosarcoma iliac blade, similar case, we have created 3D model. We have done MRI and CT scan fusion, and then we have created resection jig, that blue one. They, similarly, one more case, we have created 3D printed jig, and we got uh, in these cases. So it is difficult to get tumor-free margin in the complex pelvic tumor surgery. That better accuracy in the patient-specific jigs than freehand osteotomy in the cadaveric studies. Although the accuracy of the osteotomy versus navigation is similar in a study by Wong et al., but more time was taken in the navigated osteotomies. The, management research that improved virtual surgical planning with the 3D multimodal image for the malignant giant pelvic tumors are better. There is one more study that 3D printing technology in hip and pelvis surgery. This study proved that 3D printing and the virtual resection of the tumor. Similarly, many studies have been done on this. So, Thorsten et al. Also studied about the tumor resection at the pelvis using 3D planning and got better outcomes. Similarly, we also observed that tumor in our own, though it requires good expertise with the software, more time in pre-operative planning than usual, but surgical conclusion is that key 3D planning helps in better visualization and precision. Patient-specific jig performing precise osteotomy in order to obtain adequate resection margin, and overall 3D printing is very surgical care. Thank you. Any question?
Thank you, Dr. Abhay Meena, for your presence and presentation. Does anyone having any queries? I hope there are no queries. Once again, thank you, Dr. Abhay, for your presence and presentation. Now let's move on to the next presentation. It's from Dr. Tunji John Erinel from Federal Polytechnic, Nigeria. Hello, Dr. Tunji. Are you ready with your presentation? Hello, Dr. Tunji. Hello, Dr. Tunji. Can you please unmute yourself?
Good morning.
Good morning, Dr. Tunji. Now I'm making you as a presenter. Kindly click on the share button to share your
Good morning.
screen, please. Good morning, good morning.
Good morning. Good morning. Good morning.
Yes, doctor. Now I'm making you as a presenter. Kindly click on the screen button, please.
Good morning. Good morning. See outside and see what you do. Yeah, I'm listening. Abuja.
Hello, Dr. Tunji.
That build tó wà lẹ́gbẹ̀ẹ́ lọ yẹn lọ fi ṣe wà lókè.
Hello, Dr. Tunji. Hello, Dr. Tunji. Can you please leave the session and rejoin the again? We are unable to see your screen. I think there's a technical issue from Dr. Tunji end. So we'll be waiting few more minutes. So thank you. Okay. Meanwhile, we will move ahead with the session. Now, the next presenter is Dr. Milan Meriwan from American University of Iraq, Suleimani, Iraq. Hello, Dr. Milan Meriwan. Are you ready with the presentation?
Hello, how are you guys? Yes, I'm ready.
I'm good. Thanks for asking. Now, I'm making you as a presenter. Kindly click on the screen button to share your screen, please.
Yes, of course. Is it sharing right now?
No, it's not shared yet.
Okay.
Kindly select entire screen for sharing.
Okay. Okay. Wait. Let me start podcast. Podcast. What about now?
Yes, your screen is shared. Your screen is shared. Can you please open a full screen mode? Yeah, perfect. You can start your presentation.
Hello, everyone. I hope you guys are doing well. In this presentation, it was about the effect of fill fraction and fill morphology on shrinkage and mechanical properties of 3D printed polylactic acid PLA. It was planned for me and my colleague Nivan to share and present this presentation with you, but due to some circumstances, it's just me who was going to present it today. This presentation and this research was done at the American University in Iraq, Slimani, and supervised by Dr. Nathaniel, who got his PhD in material science. We're going to dive into our presentation and we're going to talk about the importance and how did we started and what inspired us to do this presentation. First, we're going to talk about briefly about the problem statement of this presentation. This research was inspired by a problem that we faced during our project in 3D printing. We realized that some of our parts or the printed sample was not exactly precise dimension as we expected to, especially in PLA. And we realized that this is a common situation that happens due to our samples. And we realized that it's an expected error, but there was nothing to account for. So we tried to do this research to make a relationship between the fill density with the shrinkage as well as the mechanical property of PLA. The objective of this project or this research was to identify the relationship between the infill density, shrinkage, and mechanical property for PLA, which can help us to account for any shrinkage that happened, as well as the application that we need to account for. For example, due to the popularity of 3D printing right now, in many applications such as manufacturing, even dental and medical fields. So this is a very important research to for the for the what is called for the mechanical property as well as the densities. The relevance of this research is that, as I just mentioned before, is the field of additive manufacturing is growing very quickly and being adopted in many forms and in many commercial and industrial application, including dentistry. One of the doctors that we talked who were working in dental retainers, and he told us that this is a common thing that happens in 3D printing where shrinkage and inaccuracy in dimension happens. Our shape and our samples were inspired by dental retainers, which we're going to show you in the upcoming slides. As well as this research aims to develop a structural development in 3D printing simulation at AUIS. Since AUIS, the American University in Iraq Slimani, doesn't have a lot of experience with simulation, this research would aims to open doors and classes for simulation, such as digital image coloration, as well as geomagic, which we use it during our research. Uh, Now we're gonna dive into the variables and constants of our research. The varied input parameter was the infill density. We chose three different infill density, which were the 25 percentage, the 50 percentage, as well as the 100 percentage. The measured parameter were shrinkage, as well as the strength and stiffness. Moreover, the material studied was PLA printed through a type of printer which is called Ender 3D printer. Furthermore, the constants include but are not limited to, since we cannot um, control everything. It was the printer as well as the type of the PLA that we use it, the location, the surrounding temperature, the extrusion temperature, bed plate temperature, leveling of the temperature, as well as the direction of the printing, as well as the printer speed. Now we're going to dive into the methodology. And first and foremost, we're going to talk about the tools and the techniques. First, the tools and the techniques we use at the Ender 3D printers, as I mentioned, as well as the 3D scanner. Moreover, we use it in Strong compression testing machine, GOM software, Geomagic Control X22, as well as SolidWorks. Now we in this slide, I'm gonna show you the solid work or of the our sample and our dimension. It was a U shape, as I just mentioned. It was inspired by dental retainers. We chose three different density, which were 25, 50, and 100% infill. The models were physically measured as well as 3D scanned. Moreover, software such as Geomagic Control X22, GOM software was used to compare the printed part to the design dimension, as well as to find the strength and the stiffness of the PLA. This is the printed sample as well as the speckle sample for the digital image coloration. The picture shows our sample that we got from printing. The second one, it was the speckle sample, which we got it ready for the digital image coloration. This is our result by using a 3D scanner, as well as comparing it to our SolidWorks image, which we got a simulation which it tell us the deviation in different parts. As we can see, the 100% in full got the less deviation, and the 50 and the 25, as we can see. And from this software, we got two different graphs and tables. As we can see, we got tolerance deviation, as well as a table which we compared the manual measurement to our real measurements. First and foremost, I'm gonna dive into the tolerant deviation. As we can see, the over tolerance in the 100% is much more, and it goes to 50%, and then the 25 percentage, and the under tolerance is a reverse, which is the 25 percentage and the 50 and the 100%. And it was expected from the start of our experiment that the 100% would see less shrinkage, as well as it would be constant rather than the 25 or the 50. Moreover, we also manually measurement three parts of our U shape. As you can see, the A and B and C. I'm going to go back to the other side. The A is the measurement between the internal gap, and the B is the measurement between the external gaps, and then the C is from the bottom to the top. As we can see, for the 25, 50, and 100, the internal gap was constant between all of them. The real measurement was 25, but the manual measurement decreased by 0.5 percentage from 25 to 24.9. Additionally, for the B, which is the external measurement, for the 25 percentage, it decreased from 65 to 64.9, which is a decrease of 0.5 percentage. For the 50%, it was constant, and for 100%, it actually increased by 0.5, 0.15, I'm sorry. And additionally, for the measurement of the C, which is the measurement between the bottom of the U-shape to the top of the U-shape, it was for the 25 percentage, for the 25 percentage in full, it increased by 0.5 percentage, and for the 50, it also increased by 1, and for the 100 percentage, it increased by 1.3. The usual design of the printed shape causes some interesting outcome from the scan results shown in the tables and the graphs. The inner arc appeared to be most likely surfaced to retain its design dimension, not shrink as much as the outer arc, and this is possibly because of the constraint applied to the inner arc due to the surrounding material. And this is a reference that it was a research paper that was uh, uh, did my screen got unshared? Sorry. So the reference is a research paper that was published in 2022, which is under the title of The Significance of Fundamental Methodology of 3D Printed Part for Engineering Design, Dimensional Accuracy. And our result is very similar to this research paper. As we can see from this table, they measured three different density, infill density, 30%, 60%, additionally to 90%, and the standard deviation increased as the density increased, which is similar to our result from our research. Now we're gonna go to the digital image coloration, which is very, very interesting. This is by using Instron compression testing as well as GOM software. First, we started to spackle our samples, and then by using Instron compression testing, we did the compression test, and by taking videos and pictures and using GOM, we could see the places that there's cracks as well as strain. From the picture from the 25 infill picture, the crack initiated normally from the outer side and then changing its direction to grow between the fill ligament. Additionally, the strain localized at the inner surface, resulting in buckling, while the 50 percentage strain was distributed more broadly among the multiple fill ligament. Additionally, no strain localization or buckling at the inner surface happened, which was different from the 25 percentage infill. And finally, the 100% infill, the strain was distributed broadly, crushing at the inner surface due to the compressive overload. The 100% from our compression test exhibited more force and can handle more force comparing to the 50% infill and 25% infill. Additionally, the instron was put on 1 millimeters per minute, the speed of it, which gave us these results by using our GeoM software. And from the instron compressive test and the software, we got different graphs. First and foremost, the absolute load versus displacement. The load was measured in Newton and the displacement was measured in millimeter. As you can see, the 25% infill, the load was distributed more broadly, as well as it happens in a straight line, as well as the 50%. And as we can see from the graph, the 100% infill can handle more force, as well as the extrusion or displacement. It was much higher than the 50%, as well as the 25%. Additionally, we created different graphs, for example, the infill percentage versus the mass in gram. And we can realize from our graphs, as we increase the infill percentage, the mass increases. Additionally, we created a graph which is about the peak load to mass ratio versus the infill percentage, and the 100% infill exhibited more peak load to mass ratio comparing to the 25 and the 50%. And we can see that the 50% exhibited less peak load to mass ratio, and this is might be errors since it should exhibit more than the 25, but due to our instron compressive test, it might happen it might have been some errors in it, and this is why in upcoming our research, to make it more precise, we will recreate our test to see if the same thing happens. Additionally, the peak load versus the infill, and it increased as we increased the infill percentage. For the 100% infill, the peak load was 1,639 approximately, and for the 50%, it was 685, and additionally for the 25 was 481. So it increased as we increased the infill percentage. In conclusion, we can get from this research as well as this presentation is that when 3D printing a precision part with an internal hole or a gap, such as bearing housing, designers should consider increasing the size of internal hole or gap or spacing to accommodate to shrinkage that could occur. Additionally, when 3D printing a pin or axle or other part that must fit inside a hole, designers should consider decreasing the diameter or size of the pin or other internal part, especially if the infill density is high. And we realized this due to our other projects for mechanical and machine, which we realized that as we increase the infill densities, the pin or the axle could not go into the designed hole. Finally, as the infill percentage increases, the strength of the 3D sample also increasing, which means that they can withstand greater load. And finally, as the infill percentage increases, the load to weight ratio also raises, which can tell us that as we increase the infill percentage, the sample can withstand more force per weight. This was the presentation that was created by me, my colleague Ivan, as well as Dr. Nathan. Thank you so much for listening, and I hope you guys uh, enjoyed my presentation. If you guys have any question, I will be happy to answer. Thank you.
Thank you, Dr. Milan, for your presence and presentation. Does anyone having any queries? I hope there are no queries. Once again, thank you, Doctor, for your presence and presentation.
Thank you so much. Have a nice day.
As now we are moving ahead with the session. So now let's move on to the poster presentations. The first poster presentation is from Dr. Jenep Kirimler from Trab Biotech Advanced Implant Technologies Turkey. Hello, Dr. Jenep. Are you ready with your presentation?
Yeah, I'm ready. Are you able to see my hear my voice? Is everything okay?
Yes, your voice
Okay.
is audible. Now I'm making as a presenter. Kindly click on the screen button to share your screen, please.
Okay.
Please select your entire screen while sharing. Yeah, it's perfect. You
Are you
can
able to see?
start your
Okay.
presentation.
Okay. So we prepared a real poster paper. Sorry for that. I will zoom in for the technical parts. I'm Zeynep Kırımlar from Trabzon Medical Turkey, and I continue my master's degree in biomedical engineering in Medical East Technical University also. So if I need to talk about my company, Traptech is a company working on the field of medical implants in Turkey. So we have R&D projects and R&D studies in many areas of metal and polymer additive manufacturing. We have an additive manufacturing center, and we have more than 10 metal and polymer additive manufacturing machines out there. We transfer the knowledge of the that we gained like since 2013 to our projects. Today, actually, I will make a presentation on behalf of my teammate, İpek Döş. She's not here right now. So the presentation will be show us like the results of our R&D project on craniomaxillofacial implants that can be especially used in pediatric cases. So as an introduction, craniomaxillofacial defects in pediatric patients present a unique challenge due to the dynamic nature of the growing bone tissues, and long-term implications of the implementation. Traditional materials often fall short in mimicking the biomechanical properties of the natural tissues, and may require subsequent surgeries for replacement or adjustment, like titanium ones. So in this study, we aim to address the limitations by introducing the 3D bioprinted biodegradable composite material consisting of PLGA and nanohydroxyapatite. We made a composite material from them. PLGA has been extensively studied for its biocompatibility. Okay, somebody's here. PLGA has been extensively studied for its biocompatibility and controlled degradation, and hydroxyapatite is known for its osteoconductive properties. So mixing them together and getting a composite is a really beneficial way for us, but it has also challenges. The composite is designed to be compatible with the pediatric craniomaxillofacial, like I can say CMF after that. CMF structures offering tailored mechanical properties, controlled degradation rates. In addressing the crucial factor of osseointegration, it is imperative to consider not only the material's distinct properties, but also its structural configuration is important. Utilizing additive manufacturing techniques, this study proposes the use of gyroid lattice structure for the bioprinted composite. The gyroid is triply periodic minimal, has a TPMS structure, triply periodic minimal surface structure, so it's interconnected, and it offers enhanced surface area for cellular adhesion and proliferation. Furthermore, the interconnected porous nature of the gyroids promotes nutrient transport, vascularization, and bone ingrowth. So When I jump into the methods, I can zoom in for you. Okay. We used PLGA granules from Resomer and nanohydroxyapatite from nanography. Its origin is Turkey. We get a mixture from them, like mechanically mix them, and use for our Alevi bioprinter, Alevi 1 bioprinter. It has a pneumatic system also. So initial prints were conducted with PLGA alone because Alevi WebST has its own printing parameters for just only the polymers. So we tried firstly just polymer process parameters and provided them. Also after that we optimized our printing parameters for the composite material, which includes PLGA and nanohydroxyapatites. And after that, we examined the structural porosity via SEM and micro CT. We conducted compression tests and in vitro and in vivo biocompatibility tests also. We search for the therapeutic biological agents and the antibiotic release of the structure also. So here are our results. You can see the FDM, pneumatic FDM printed gyroid structures of us, the composite material. And in the figure 2, you can see the antibiotic release kinetics of the gyroid structure. We used vancomycin. And the figure 3, you can see the interactions of human fetal osteoblast cells cultured on the 3D printed composite material in the 4th, 14th, and the 21st day of it. In the figure 4, you can see the time-dependent variation of viability of the osteoblast cells for 28 days. And we did also alizarin red mineralization analysis for 21 days. So it will be a really quick poster presentation. To jump into the conclusions and the discussion parts, we saw that the PLGA and the nanohydroxyapatite material surface an increasing number of the spread of the cells and the number of the cells, the size of the cytoskeletons, extensions required for cell and cell-to-cell adhesion. And also it was observed that the osteoblast cells proliferated from day 4. And the gyroid structure and the PLGA and nanohydroxyapatite composite material presents linear antibiotic release, which is the situation we wanted. And the gyroid form that we designed for our project, the porosity and the pore sizes and the material composition itself, it's very uniquely suitable for the pediatric implant applications rather than the titanium ones. So also we want to acknowledge that this project is supported by TÜBİTAK, the Scientific and Technological Research Council of Turkey. And we also have special thanks to the Middle East Technical University, Dilara Göksutamay and Professor Dr. Vasıf Hasırcı for the biological analysis. So that's all. If you have any questions, I would like to answer.
Thank you, Dr. Joanna, for your presence and presentation. Does anyone having any queries?
Okay then. Thank you for
I
your
hope there are
time.
no queries. Once again, thank you, Dr. Trana, for your presence and presentation. Now let's move on to the next presentation. Is from Dr. Jeevan Deep from Mishra from IPS Academy, College of Pharmacy, India. Hello, Dr. Jeevan Mishra. Are you ready with the presentation?
Yeah, very, very good afternoon, ma'am.
Good afternoon. Now I'm
Yeah,
making
ma'am.
you as a presenter. Kindly click on the screen button to share your screen, please. Have you got any pop-up window on your screen? Hello, Dr. Jeevandeep, are you there?
Yeah, ma'am.
Yeah, your screen is shared. Can you please share again?
Yeah, ma'am. Now sharing.
Yeah, your screen is shared. Can you please open your presentation?
Now visual, ma'am.
No, not yet.
Ma'am, visual.
Your screen is shared, but your presentation is not visible yet. We are able to see only a blank screen. Your screen is visible. Or can you please open your presentation?
Yeah, ma'am.
Can you please open your presentation? Minimize that and please open your presentation.
Now visual.
Your screen is visible, Dr. Jeevandev. Can you please open your presentation?
Yeah, ma'am. I opened my presentation.
No, then please unshare and share the entire screen while selecting. Uh, Please unshare and share the entire screen.
Yeah, I click on share but screen.
Don't choose the application, just select the entire screen for sharing.
Entire screen. Yeah.
Yeah.
Share. Now
Okay,
sharing,
now open
ma'am.
your PowerPoint presentation. Yeah, your screen is shared. Can you please open your presentation?
Yeah, ma'am. Now open.
Now it is perfect. You can make it as a presentation mode and start your presentation.
Yeah, thank you, ma'am. Very, very good afternoon and all to present here. I am Jeevan Mishra from Indore, India. First of all, I want to thank 8th European Congress on 3D printing and additive manufacturing for giving me chance to present the poster on 3D printing technology, pharmaceutical delivery, contemporary advancement and application. So let's I start. First of all, introduction. 3D printing is an emerging field of that can be found in medicine, electronic, aviation, and other fields. 3D printing technology are consistently implementation and novel fields, laying fundamentals or new commercial revolution. 3D printing aim to provide tailor-made tablet as per the patient necessity. 3D printing is a particular technology that turned into the first described by the way means of a Charles Schulz in 1986. 3D printing technology has a fantastic embryo and of a percentages shape concept of a especially polypill concept. In 2015, the US FDA Drug Administration approved the sputum of the primary tablet for the treatment of epilepsy in seizures. 3D printing impact on the pharmaceutical and medical devices industry as well as capacity expansion, quality control issue and regulatory issues. 3D printing technology we want to permit on demand of manufacturing products, personalized doses, drug combination of a geometrics and release density. There are many identicals of a 3D printings like cost, safety, versatile, efficacy, user friendly, and stability. Have many advantage in 3D printing. It will like of a accurate dosing in a mighty pills of a which administration at a small dose, and also they help in a eco-friendly of a production in the process of the fabrication formulation. With 3D printing has no wastage the pollutants the atmosphere. This is also help in a suitable combination with of a replicate dosing of augmentation remedies may be tailor-made chance affected in the person. In figure number first, they are the show the product by 3D printing, and there are there are many dosage form like polypills, hydrogel, fascicle marks, and nano capsules, implants, tablets, no, nose patch, capsule, film, etc. In these formulation of a used of various types of method, they are given below. And now I'll discuss about the types of a 3D printing. There are many types of 3D printings like laser based starting system, thermal inject printing, fused deposition modeling, and power based inject printing. Now I discuss about the laser based starting system. Laser based starting system is a temporary based on the totally principle the standard photopolymerization, in which the free atom molecules or ion liberated after the interaction among the inators and ultraviolet light. Laser-based starting system, it is divided into two types. First is a selective laser-based starting, a second is a stereolithography. Selective laser-based starting system is based on the power-based inject printing, and the first utilization the selective of a laser staining for the pharmaceutical betterment with the inside the fabrication of the polycaprolactones, primarily based on the totally drug delivery system. Now I talk about the stereolithography. Charles Hooke introduced the stereolithography in 1984. Stereolithography is a method that are used to contract medical and computer parts and which are very costly. Stereolithography techniques associated the use of a polymerization and footage of a 3D designs. A controgenous ultraviolet rays of over photopolymerization, liquid floor by floor fashions a chemical reaction that causes of a gelatin in a displaced area. Now I talk about the type second thermal inject printing. Thermal inject printing is a proposal of the contamination of a medicine ensure for the processes computer operators thermal inject printing and carry of the thermal inject printers. Thermal inject printing use of a thermal radiation in a piezo effect that deposited small bits ink on the medium of the contemporary with low direction feed the printer. The ink discharge from the nozzle applying the consolidation. Now I talk about the third type, fused deposition modeling. Fused deposition modeling help in the manufacturing of a delay release of a printed of a without outlying of a gresto resistance coating. They are also help in of a tailor doses medication. This method is a most familiar and economical types of printer. This is the analogous to the thermal inject printing. They are the use of a thermoplastic material. Infused deposition modeling may be enforced of a several doses shaped are tailors of a polymer is the parts of the implants and zero order release tablets of a surrounding coat tablet orally disintegrated tablet. Now fourth type is power bed inject printing. Power bed inject printing may be a separately prototype additive producing of a technology for creating object of a represented by digital knowledge of a similar to computer aided design files. The object are the concept for the spreading of the expensive for the fine materials that are the square in light region printing binder solution using inject type of nozzle. They are the divide into two techniques. First is a continuous jet printing, a second is a drop demand printing. Continuous jet printing is a stream of ink droplet continuously injected by a nozzle. Ink column under pressure, charge droplet affected and deposited using electric field. Drop on demand printing is a high costly than of a continuous jet printing because it produce of a droplet when are deposited only when required. This result is a less wisdom. Continuous jet printing is a based on a heads of a penolize electric inject and thermal inject. Drop on demand is a based on the substrate, drop on solid and drop on drop. Now in figure number 7 of a show the current 3D printing technology pharmaceutical formulators drug delivery sorry in these are the and these are the published of our research in year 2010 to 2019. We can see that of a fused deposition modeling of a more used as compared to the other methods. Now I talk about the chip dose technology. Chip dose technology is developed by a Preka Pharmaceutical that help in the manufacturing of tablets with drugs loading capacity and instant of a over disposal tablets. High dose load. This is the high dose loading capacity up to 1,000 mg of drug. A wide range of test masking and capabilities. Rapid disintegration in a second when in contact with water. This is the selection of bind of particle together thin porous layer. Then liquid is dropped on the powder, and this is a selective binds particle together in a thin porous layer, and this porous is represented of a specific number of times and add more layers based on the doses, building the product from of a bottom to the top. There are many applications in use of a 3D printing. First, we have a commercially accessible of a 3D printing. Spreadum is I talk about the already is Spreadum tablets. Spreadum so within the aids of using of a African pharmaceutical adopting of a chip dose technology primarily based on the totally on the power weight inject printing. The pharmacologically effectiveness of a spreadum change into the assembles of the propylenics of and conventional tablets. Second application is a cancer treatment of a currently of a PCL and 5-fluorouracil loaded patches have been appropriated printed and insert directly into the pancreatic tumor. Now, third application of a novel doses form in novel drug delivery system. A novel doses form of a like of a microcapsules, nano suspension synthesis, extracellular matrix, antibiotic printed micropatterns in a mesospores and bioactive glasses, scaffolds, and explosive types of multi-layered drug delivery devices are used of few. These are the few examples of a novel doses printed by using of a 3D printing technology. In order to offer produce of a paclitaxel microcapsules with of a precisely of a defines the control forms only and logos of a piezoelectric inject printing system. 3D printing polypills, the captopril and nifedipines within of a side in treatments of hypertension and glizapridines used as a within side in treatments of type 2 diabetes. Now, last last application use is a personalized treatment. Salicylic acid filter of a nose shaped of a mask anti-acne treatment heads of a quickly confident introduction. The subject of a free scan of a captures imaging projected into the AutoCAD's application in no segments and then fusion. And this personalized medicine I talk about given in the figure number first. Now I conclude about my poster topic. 3D printing has become of the convenient for the pharmaceutical sector, exponential and personalized medicine specialization in the patient. FDA approved the first 3D printing tablets freedom change into the massive milestone in the technology in history. 3D printing allows manufacturing the oral drug delivery system and enhance the solubility release of a fully solubles and drug. And 3D printing help in the development of a pediatric and geriatric dosage form. The use of 3D printing drug delivery systems are currently on the rise of creating the possibilities that of a 3D printing and traditional pharmaceutical technology will one day of combine to of expand the areas in which can be used. Thank you, everyone. Thank you.
Thank you, Dr. Jeevan Deep, for your presence and presentation. Does anyone having any queries? I hope there are no queries. Once again, thank you, Doctor, for your presence and presentation. Now, let's
Thank you.
move on
Thank
to
you.
the next
Thank
poster presentation. Is from Dr. Joinab Krimler from Trab BTech Advanced Implant Technology, Turkey. Hello, Dr. Joinab. Are you ready with your presentation?
Okay, I'm ready. Hear me again.
Yeah. Now I'm making you presenter again. Can you click on the screen button to share your screen now?
Okay, everything's okay.
It's perfect. You start your presentation.
Okay. The second R&D project of us is the comparison of EBM and the SLM processes for metal additive manufacturing, especially for implants and implant surfaces, trabecular implant surfaces. So we in the study we compared the 8 different lattices and the EBM and SLM processes of them. So we conducted both mechanical in vivo and in vitro tests. So for a quick introduction, we know that lattice structures find a very widespread application area on implant surfaces because they can create trabecular intersections and they can mimic the cancellous, the spongy bone you can see in the figure 1. So the aim of the study is as I said, conduct a comprehensive analysis of different types of lattice structures that we manufactured by EBM and SLM, which is electron beam melting and selective laser melting technologies. We compared the producibility, production precision, as well as mechanical and biological properties of the lattice structures. The methods, actually, here you can see some of the lattice structures we produced. Firstly, we select 8 different lattice unit cells currently available in the anthropology library. In our metal implant applications, we usually use anthropology and its library. It's also open source. The lattice structures have been designed with respect to 3 parameters. We designed them according to their porosity percentage, strut thickness, and cell size. Strut thickness is important for us very much because the production precision of SLM differs. So the minimum strut size, the smallest strut size we could reach through EBM is 0.4 millimeters. Also, for the cell adhesion and proliferation, we know that the porosity is important. We vary the porosity from 60% to 80%, like 65, 70, 75, etc. We prepared a Python wrapper script, so and then we implemented on the anthropology. So we automized the process for the cell sizes and the porosity relationship. So after that, we conducted finite element analysis and select the 2 of the lattice unit cells according to their elastic moduluses. We can we try to select the 2 of the lattice unit cells according to the elastic modulus of the bone, cancellous bone. So nearest 2 of the lattices selected for further study. Also, we produced the 2 of the lattice structures which are graph diamond and custom unit cell. Custom unit cell is the one we designed. So before manufacturing the lattice specimens, we conduct another study for getting the optimum process parameters of it. And after that, we produced bulk samples and conducted Archimedes tests and microporosity, micro-CT analysis of them. So here you can see the lattice selection criteria for us. The line is the elastic modulus of the cancellous bone, and the 2 we selected are the upper. Are you able to hear my voice? Sorry. Okay, I think there's a problem with my headphones. Okay. I cannot hear you right now, but I will figure it out, I think. Can you give me headphones, please. Okay. Okay.
Hello, Janet. Hello, Janet.
Sorry, are you able to hear me now?
Now you are audible. Or from past 5 minutes, you are not audible.
5 minutes?
Yeah.
Okay, are you able to hear me now?
Yeah, you are audible now. Can you continue where you have stopped?
I think my headphones are dead. Sorry for that.
Okay. Okay.
But I can continue if my voice is okay.
It's perfect now. You can continue.
Okay, okay then. So where should I begin again?
Can you begin with this session from beginning?
Beginning? Okay.
Yeah, not from beginning. The next session you have started. You can the methods, I
Okay.
guess. Mm.
Okay. So for the methods, we selected 8 different lattice unit cells, and we conducted a finite element analysis of them and selected 2 of them for the further study. So here you can see the selection criteria of the lattices. The line is for the elastic modulus of the cancellous bond, and the 2 upper are the unit cells we selected for further study. Before manufacturing them in EBM and SLM, we also conducted another study for getting the optimum process parameters, and for that we tried different process parameters and conducted Archimedes tests, and also microcity. We get the microcity images of the samples, so we decided the optimum process parameters after that. Sorry? Okay. We also heat treated the SLM samples because we want to observe the beta phase similar to the EBM samples. Is everything okay? Are you able to hear me? No, I think.
Yes, we can.
Okay. Okay, thank you so much. We conducted density tests and microstructural analysis that I said. Also, we searched for the strut thicknesses and the free powder particles. Also, you conducted compression, cytotoxicity, and also integration tests on these 2 lattice cells. In the results part, you can see the SLM upper and the EBM microstructures the below. So some of the SLM produced samples, we could see the honeycomb structure, unlike the EBM. Also, the lack of fusion areas was more intense in the EBM process. So for further study, we designed 2 samples, one for the mechanical test and the in vitro and biological tests. So you can see our biological test samples and the mechanical test samples after the compression test. The images shows us actually the EBM samples are cakey, and the strut thicknesses we designed as 0.4 millimeters, but when we measured the strut thicknesses of the EBM samples, they were around 600 microns. So also you can see the unsintered and semi-sintered powder particles of EBM. Actually, these 2 are the same structure, same STL file that we uploaded to the machines, but the production precision of the SLM is more accurate. The second image, you can see the cells, day 7 of the cell seeding, the EBM on the left and the SLM on the right. So last image is the 14th day of the cell seeding process. The proliferation of the cells actually resulted positively, but we thought that because of the EBM samples having more phases to proliferate, the cell viability we get was more. So you can see the variation of the viable cells number by the experimental groups. The cell viability is higher in the SLM, EBM. So, but it's not the results didn't show us the EBM is better. So in the figure 11, you can see the viable cells in the metal samples. Actually, we firstly compared the EBM and SLM processes in vitro tests. After that, we compared the two unit cells we selected, which are custom and diamond lattices. So the results showed us after the mechanical tests and SEM imaging, the strut thickness we designed is 0.4 millimeters, but the strut thicknesses in EBM samples was 0.6 millimeters. So when mechanical test results were evaluated, it's observed that the variation between the compressive strength of the EBM was higher, and elastic modulus was higher, much higher than the SLM samples. So we thought that it will be due to the high strut thickness and the presence of non-sintered or semi-sintered powders in the geometry in the EBM samples. The results of the in vitro tests, EBM and SLM. Firstly, we compared EBM and SLM. Cell viability and EBM samples was higher, and then we thought that also is due to the higher surface area on which cells could adhere more. So after in vitro tests, we conducted osseointegration tests with pre-osteoblast cells, and ossification and mineralization results were evaluated. And we, with the mineralization results, we saw that EBM diamond samples had a more equal distribution than the other groups, and also diamond lattice unit cell better than the custom unit cell. Also, in addition, SLM samples show statistically higher mineralization activity than the EBM samples. So also we conducted in vivo examinations like the according to the ISO standards, the biocompatibility standards, and SLM process did not show any toxic effects. So in conclusion, we conducted a comparative study on the trabecular surfaces of metal implants produced by additive manufacturing, and we found that SLM process more precise and design accurate products than EBM process, and SLM is more suitable for this purpose when the success of dust cleaning is evaluated. Our study is also provided and supported by TÜBİTAK, the Scientific and Technological Research Council of Turkey, and you can see the project number over here. Thank you so much for your time. That's all.
Thank you, Dr. Joanna, for your presence and presentation. Does anyone having any queries?
Hello.
Hello.
Yes, Dr. Irfan, you can ask
Yes,
your query.
thank you. First of all, thank you, dear Jenny, for your nice presentation. So you explained very well about the comparison between SLM and EBM. So have you published paper regarding this direction?
We haven't published any papers yet because the confidentiality
Oh,
agreements
yes,
regarding our company.
sure.
But we can mail like each other for the further details if it's convenient for you.
Okay, thank
If
you.
you okay, thank you so much
Okay,
for your question.
okay, sure.
Thank you, Dr. Irfan. Does anyone having any queries more?
Can I have a copy as well, please? Hamid,
Copy of the poster.
of the presentation.
Okay, for sure.
Thank you.
Sure, will be the program manager will be sharing you, Dr. Hamid. Uh,
Okay. Yeah, it's okay.
uh,
Thank you.
okay, does anyone has any more queries now? I think then there are no more queries. Once again, thank you, Dr. Joanna, for the presentation. Now let's move on to the next presentation. It is a oral presentation from Dr. Shan Mohammed from University Polytechnic, AMU, India. Hello, Dr. Shan Mohammed. Are you ready with your presentation?
Yes, ma'am. Yes, ma'am.
Okay,
I'm
now
ready
I'm
to
making you as a
present the
presenter.
presentation.
Kindly click on the screen button to share your screen, please.
Okay.
I have made you as a presenter now.
1 minute, ma'am. Am I audible, ma'am?
Yeah, you're audible. Your screen is visible. Can you make it as a presentation mode from beginning?
Okay. Hello, gentlemen. My name is Shan Mohammed. I'm from India, and here
Excuse me,
I'm
Dr.
presenting my
Chan.
paper.
Your
Yes.
screen is not in a full screen mode, and can you please? We are able to see
Okay.
only the 11th slide. I think. Can you please go to the GoToMeeting app and unshare and reshare with the entire screen sharing, so we can able to see your full screen. I think you have
Okay.
selected only application, so that we are unable to see your presentation mode now.
Now, ma'am.
Yeah, your screen is shared. Please open your PowerPoint presentation here.
Okay.
Can you
Now it's
make it in
clear.
a presentation mode? Yeah, it's
Right.
perfect. You can start.
Okay. Here I'm presenting my paper on analysis of 3D printing defects in polylactic acid parts. Basically, 3D printing is an additive manufacturing technology which is used to develop 3D objects in industries, and industries use this technology for increasing our productivity. And in 1981, it's only an idea which is given by Hideo Kodama of Nagoya Municipal Industrial Research Institute in Japan. And further, in 1986, an American engineer named Charles Hull created a prototype and filed a patent on SLA technology of 3D printing. And here I will show my work on fused deposition modeling, widely used in industries to prepare the prototype jigs and fixtures and other things which are used to increase the productivity of industries. According to statistics, the worldwide market for 3D printing products increasing and expected to exceed 40 billion US dollars by 24 will get. Now in this our work we use polylactic acid parts. PLA is a thermoplastic, and as as everybody know, PLA has low printing temperature compared to other thermoplastic materials. PLA is easily pigmented and comes in diverse range of colors, and there is no need to any closed chamber for working with PLA. And fused deposition modeling is a method which is used in our work on to find the defects in 3D printing, 3D printed parts of PLA. FDM 3D printer uh, works on the manner of layer by layer manner or additive manner, and the material is fused through the extruder in layer by layer manner, and on the platform, and the product will get. Now this is a full setup of FDM 3D printer, and this work this type or this pool test of material, and this product will working on this printer get working, and this is a process of generating an infill structure of product, and here clearly visible that the product is making by addition of successive layers. Defects in polylactic acid parts are very important topic of this paper. And first of all, warping is a defect in PLA parts, which is mostly visible in other material parts, but in PLA, it's very less. But the larger part, the large parts of the PLA showing the warping defects. So, warping is a term used in 3D printing to describe when the first layer of part is deformed and detached from the printing surface. Warping in 3D printing shows up mainly in large parts. The thermal stresses in the part become more powerful and end up pulling the part off at the corners. So in PLA parts, PLA is the material, as you know, least warping that exists as in 3D printing. Because of it has the lowest temperature, lowest thermal expansion coefficient of all. So when PLA parts cool, they shrink less than another materials. Now we will move on cracking defect, which is a next level of warping defect. When cracking is another problem closely related to the warping, which appear in the intermediate layers of the part. In general, if a part has cracking, the first layer will always be affected by the warping as well. And the cracking is caused by stresses induced during the cooling of the parts. During the cooling of part in the intermediate layers, if welding between the layers is not good enough, these stresses end up spanning the layers and leave horizontal surface and cracks. So, and we will move to the layer shifting. Layer shifting is also a defect in PLA parts. During the printing, most 3D printers use an open loop control system, as we know, which is a fancy way to say that they have no feedback about the actual location of the tool head or the extruder. And the printer simply attempts to move the tool head to specifications and hope that it gets there. In most cases this works fine because the stepper motor that drives the printer are quite powerful, and here in significant loads to prevent the tool head from the moving. However, if something is go wrong, the printer would have no way to detect this. What's going on? What's going here? Unfortunately, once this error occurred, the printer has no way to detect and fix the problem. And in Z bubble defect is also also we can say this is a ribbing. This is a ribbing. It refers to the appearance of obvious obvious lines on the interior surface of this. As you can see, marked area, the ribs are showing here, and regular intervals. This print quality defect is relatively uh, rare, but is no less important to fix. So we have to fix this uh, to increase our productivity of our industries, and to improve the quality of the products, because productivity is increase. If the quality is not good, then productivity will not increase. So we have to fix it. So now stringing is the last and very important defect in the 3D printed PLA parts. Stringing happens when small strings of filament is left behind on 3D printed objects. This is typically due to filament dripping. There's here you can also say this this marked circle show the stringing defect, and dripping out of the nozzle when extruder is moving to extruder location. And because in this situation, extruder temperature may be high, extruder retracting speeds of the printer may be high or low, very low, and retracting distances may be high or maybe low. So this is the causes of stringing defects. So now remedies, results of our results of our work are remedies of warping defects. As you can see here, uh, by raising the temperature of the bed, we can improve the quality of the product by removing or by reducing the warping defect. And uh, by providing closed chamber, because PLA parts has no required closed chamber. But when we work on work on FDM 3D printer for producing the PLA parts, so we have to use a closed environment of the around the printer to improve our quality of the product. So also we can use another accessories like a Campton tape, hairspray, T-lac, and Dimafix. These are the those accessories which are used to prevent the uh, prevent the product to the warping defect. So now remedies for cracking defects. As we see already, the cracking defects occur in the intermediate lines, and in this situation, first thing is product will product will defected to the warping defect. So here keep the print at a higher temperature. If we print at do the print at a higher temperature, then we have to use the closed area or close environment of the 3D printer. Raise the extrusion temp while raising the extrusion temperature a little to improve adhesion between layers, because temperature, by increasing the temperature, we can improve the adhesion between two layers, and our product get improved and prevent with the cracking defects. And avoid room temperature variation by because in our 3D printer works on in a room or in a hall. So we have to control the room temperature or the environment around the printer to remove or to reduce the cracking effects. Here remedies for layer shifting defects. As we know, speed of the extruder is very important thing during the 3D printing, because if the speed of the extruder is high, then we and temperature is low, then we see the material get solidify, and the nozzle will get clogged, or stop the extrusion of the material. And by controlling the tension of the belt to prevent the slipping. And tension is the here tension of the belt. This first figure shows the belts, moving of the belts here. This first figure shows the moving of the belt. If the tension of the belt is not high, or not particular or specific for the 3D printing, then we will get the stringing defect or cracking effect, and the defect. And specifically here, uh, the yes, yes, sorry. uh, by checking the tight the motor fasteners, and here we use stepper motors. If motor fasteners are not tight or not it means that uh, here stepper motors nuts and nuts are maybe right tight fully or slightly, because if these are fully tight, then we will get also the stinging effect. If we slightly tight, then we get another defect. So we have to tight the motor fasteners as per the requirement, control the motor spinning, and control the electrical current is high, then we get speed of the extruder will also increase, and we get this defect. So we have to control that. Remedies for Z bubble defect. By this is here all maybe understand this from figures 11 and from figure 12, because the figure 11 shows the setting of the stepper motor, which is for the mm, uh, improving or reducing the to prevent the product from the Z bubble defect, because this Z bubble defect directly related to the misalignment of the uh, uh, Z axis. If Z axis is misaligned, then we get Z bubble. Otherwise, we will not get the any Z bubble type defect. So by tightening the eccentric nuts on the hot end mount, and POM wheels, like figure 13 show the POM wheels, and these wheels are showing work when the extruder moves in Z along the Z axis, Y axis, and X axis. So by examining this POM wheels, we can also find the problem, and by finding the problem, we can find the solution and get Z bubble defect uh, remedies. Remedies for stringing and PLA parts when it is retracting speed. As we know, as I can as already said that this is a retraction speed. Retraction settings are related to the material, related to the material, when will material come into the extruder, and the extruder how many times take how many times to extrude them in on the platform of the printer. Set the temperature as per the requirement. It means if the temperature of the material which is extruded from the extruder is very high, then we will see the this mm, material get flowing on onto the platform of the 3D printer, and we will get many defects, and we will not get the shape as per the requirement. So control the travel movement of the extruder. It means we have to control the extruder movement. It should be according to our requirement, and according to our G&M codes. Otherwise, basically 3D printing works on the basis of GM codes. But if our setting of the if our the setting of the 3D printer is not good, then extruder movement of the extruder will not get as per the requirement and as per the GM codes. So at, uh, at the conclusion, many tips and tricks have been practiced and suggested so that we can remove defects which occur during 3D printing process. Advance in 3D printing technology can significantly change and improve the way of manufacture products. According to statistics, the worldwide market for 3D printing products and services is anticipated to exceed 40 billion US dollars by 2024. In the next 10 years, additive manufacturing is going to establish its place as the manufacturing technology which is going to support the transition to a sustainable and resource efficient civilization. These are the references. Thank you. Thank you for your attention.
Thank you, Dr. Shan Mohammed, for your presence and presentation. Does anyone having any queries? I hope there are no queries. Once again, thank you, Doctor, for your presence and presentation.
Thank you.
Okay, now let's move on to the next presentation from Dr. Chunji John from Federal Polytechnic, Nigeria. Hello, Dr. Chunji, are you ready with your presentation? Hello, Dr. Chunji. Can you please unmute yourself and hello, Dr. Chunji. Hello, Dr. Chunji. Hello, Dr. Chunji. Can you please unmute yourself? Hello, Dr. Chunji. Can you please unmute yourself? Hello, Dr. Chunji. Please unmute yourself. Am I audible to you? Can you please ping any message in the chat box so that we can know about your status? Well, we are unable to reach Dr. Chunji as there are some technical issues from his end. So by this we come to the end of day 2 webinar, and I will be glad if you could join us in next in-person conference which is scheduled in October London, and the dates will be informed to you by email. We'll be very happy if you could share us your opinion and feedback with us. Thank you. If you have any queries, we can reach to the program manager. He will help you out with everything regarding your queries. And the certificates will be sent to your mail by after the conference end. Thank you.